Hi, welcome back. So today we are going to continue our frequency analysis of new FFT. I spent a lot of time in the last videos using Ubuntu, of course, to do MATLAB and also perform some FFT and explain what new FFT is trying to do. What are the expected outputs? You will get a complex frequency and gain kind of a thing, and you will need to actually it will be given to you in terms of frequency bins. Okay, so remember I was talking about this last time, that what new FFT will do, it will give you an x of omega, and that's equals to the discrete Fourier transform, and this is what the discrete Fourier transform looks like there. F of t e minus I omega t dt. Okay, this is what the discrete Fourier transform, or the Fourier transform in general, looks like. This is the continuous version because it's an integral. Time is continuous. But of course, when we do it in MATLAB, time is not continuous, it is discrete. You have you have time at 0.1 seconds, 0.2 seconds, and it's not a continuous flow of time. So instead of using integrals, we use a summation instead, and that's what the new FFT algorithm is doing. And yeah, new FFT helps us to perform FFT on non-evenly sampled times. Okay, so last video actually was saying that when you have new FFT, you will take, okay, maybe I shouldn't use f, I should use x of t. It's less confusing. Yeah, so let's do x of t here. X of t. Alright. When you do this new FFT, you will get an array. Okay, when you do this new FFT, you will get an array of these transform versions. This will be a complex number, as I said before. The phase will be described by the ratio of the real part to the imaginary part. I didn't derive it rigorously, but you can do that. We can do that in some other video if you want, but I'm pretty sure other people have already done the videos up, so I'm not going to do it as much here. Or at least not in this video anyway. So what you'll have is an array, okay, and if you have, let's say, n data points in x of t, so like let's say from time equals to 0 to 1000 seconds, you have 5000 data points, for example, n equals to 5000. What new FFT will do is that it will return an array which is 5000 data points long, okay. But it will not give you the corresponding frequency array. It will not give you the corresponding frequency array. Okay, it will not give you the corresponding frequency array. You will have to do that yourself. So before we continue, let's just put some context to it. Let's see how new FFT will work. Yes, and CLC. Okay. Now, again, we have cleared the workspace, and what I have here is time domain data of two things. Okay, our two signals. One is the inlet temperature, one is some outlet temperature of some industrial process. Okay, and I have this inlet temperature oscillating with respect to time. So this will be my so-called what do you call that? My so-called inlet input. Okay. So if you want to put a FFT to this, okay, you want to do a new FFT on this data array. First thing you got to do is to import the array first. So we do a CSV to array. So let's do table, because what CSV to array will do is to I explained it before in the first two videos. CSV to array converts a CSV file into a table file because there's some text in there. Okay, or table to array. No. See, let's see here. I kind of forgot the syntax. Yes. Read table. Yeah, first thing is to do something called read table. Read table. Okay, so the table is read, so you have a lot of values here, but it's in a table format. It's not in an array format, which you can use it. It's not friendly with MATLAB functions, so you need to convert it into an array. So we use the table to array function. Array equals table to array table. So this is the table we imported from CSV, and then we can convert that into an array. And once it's in an array form, we can start to perform the new FFT. So what are we performing? This is the time part. Of course, now this is evenly sampled, so but you know, we don't always have cases where data is evenly sampled. So we'll just input in the time data, okay, according to the MATLAB documentation. We will input in the X data first, followed by the time data. What is X? Okay, X is your time domain data here. In this case, it will be this column here, the inlet temperature column. So let's put X equals to array every row, and I want the second column. Okay, and time equals the same thing, array every row, the first column. Okay, and then I'll just demonstrate the new FFT code, which the syntax is, okay, you want an array, we call the array Y. It will be 20,000 elements in there because our X array was 20,000 elements. So when you perform new FFT, non-uniform FFT, fast Fourier transform, it will return an array which is the same dimension as this X, okay, which you put in 20,000 data points long. So Y equals new FFT, X and T, and there you go. Okay, so the new FFT runs very quickly, and you'll see there's a complex number. Okay, again, the phase data is captured by the ratio of the real to the imaginary part. The magnitude data you can just use to plot, and you will get the spectrum plot. So if you have okay, magnitude of X of omega. And this is the common plot that we like to see. You know, we have peaks of data which you will see over here. Okay, this is the end result we often want to get. So let's say this frequency is what, 3 hertz. Okay, 3 hertz or 3 radians per second, depending on whatever unit you want to use. Okay, so it'll say, okay, here 3 hertz is one of the most important frequencies in your time domain data. So that's how we actually visualize it using this plot over here. Okay, but we are not quite there yet. Okay, the only thing that new FFT returns us is just a long series of complex numbers, which we cannot do anything about. Okay, so now we need to come up with the frequency column. And last video I actually showed you that yeah, you know, new FFT will actually give you, since new FFT actually gives you the complex number, sorted according to something called frequency bins. Okay, I'll just say again, there will be complex number here, and these complex numbers are sorted according to something called frequency bins. And the frequency spacing between each frequency bin is actually something to do with the sampling frequency. Okay, so what's the frequency spacing between each bin? You need to consider your sampling frequency first. Okay, and the sampling frequency I actually went through the last video. The sampling frequency is I will estimate using delta t, okay, or rather n, which is the number of points, over delta t. This is the estimate of the sampling frequency. Okay, so your sampling frequency will be the maximum frequency. Okay, so this is to correspond to your sampling frequency. It is the maximum frequency you can plot up to, because any frequency higher than your sampling frequency you cannot capture. Okay, and in fact as I was sharing in a few videos back, there will be sort of a mirror image at this point called fs over 2. Okay, so your peaks are being mirrored across this line, fs over 2. And this is something again called Nyquist frequency. Why is it called Nyquist frequency? Because this guy here actually contributed a lot to frequency response analysis, and I'm guessing he had a big part to play in, you know, researching all of this, and this was so-called named after him. Okay, oh yeah, I think it's a him. Back in the day, you know. So yeah. So so you can only sample up to Nyquist frequency. Okay. And your last frequency bin will be the actual sampling frequency itself. Okay, your last frequency bin will be your sampling frequency, or you know, slightly below, depending on how you want to do it. Okay, so your array, your frequency bins actually go from bin equals to 0, bin equals to 1, bin equals to 2, dot 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 dot, all the way to, if you have 5,000 points, you have the 5,000 frequency bins. Okay, concrete example. Okay, go back to MATLAB. You see that the new FFT actually returns us complex numbers across 20,000 complex numbers, because that's the number of samples we have. And these 20,000 numbers, these are like frequency bins. So this is frequency bin number 1, frequency bin number 2, frequency bin number 3, all the way up to frequency bin number 20,000. Okay, so great. I mean, new FFT is good. It sorts out the complex numbers which represent the gain and phase according to frequency bins. So what's the spacing between each frequency bin? I think I discussed it last time. It's actually fs over n. Okay, it's approximately fs over n, or yeah, fs over n. Fs over n is actually equals to 1 over delta t. And that actually makes it very convenient for us, right? Because 1 over delta t, that is the spacing between frequency bin 1 and frequency bin 2. So frequency bin 1, usually it's a 0 Hertz. We call this the DC component. Okay, again, we call this the DC component because you know, all these Fourier transforms are often used for signal analysis in electrical systems. So amplitude and of the current and the voltage are often used in this frequency response. And when the frequency is 0, it corresponds to the DC. Okay, corresponds to DC. Okay, so let me clear all of this up. And again, I'll say that, you know, fs over n equals 1 over delta t, and this is the spacing. It's very important, spacing between each frequency bin. Okay, spacing between each frequency bin. All right, so we want an array. We want an array starting from, let's say, 0 Hertz or 0 radians per second, whatever unit you want. You go all the way up to about, okay, whatever your sampling frequency is. If your sampling frequency is 2 Hertz, then 2 Hertz will, around 2 Hertz will be your last number. Okay, so, and then everything in between will be evenly spaced. Okay, even spacing. So this is what we need to do for the new FFT. We need this kind of array. Okay, how do we generate this array? Okay, there are a few ways. You can use a line space or whatever. Okay, so line space is one. I prefer a simpler method. All right, so I won't use line space. Okay, I'll use this thing. Okay, let's have a rolling numbers from 0 to 20,000 minus 1. Okay, because 20,000 minus 1. Okay, we start from frequency bin 0 or frequency bin 1, which we will have a frequency of 0 Hertz. Remember, the first frequency bin should always have a 0 Hertz. Okay, 0 Hertz. it corresponds to 0 Hz because it's the DC component. Then it will go all the way up. Remember, there are 20,000 frequency bins, right? So the last frequency bin cannot be number 20,000. It has to be 20,000 minus 1. So I will have a long matrix of this number. Okay. So this is how you go. 0 to 20,000. Okay. Again, the syntax is this: 0 to 20,000 minus 1. Okay, because we have 20,000 frequency bins, but you need to minus 1 because we start at 0. We don't start at 1. So that's how we get a running number from 0 all the way up to 20,000. Okay. And what is the next step? Okay. So remember the spacing between each frequency bin. Okay. The spacing between each frequency bin is fs over n. Okay. So fs over n, or 1 over delta t. Okay, what is the delta t here? Okay, 1 over delta t is your initial final time minus initial time. So I don't need to do some mental acrobatics. I already have a very simple formula here. 1 over delta t. So 1 over okay, let's see how long this data sample is. Okay. Yeah. Okay, so this data sample is 10,000 seconds long. Okay, all this is in seconds. All these units are in seconds. So 1 over 10,000. Okay, 1 over 10,000. So let's do 1 over 10,000. Okay. Okay. Frequency array equals 1 over 10,000 times answer. And answer is this very long running series number of columns. So let's do that. Let's see the frequency array. It goes from 0 and goes all the way up to around 2 Hz. And this is actually what we want. Evenly spaced the frequency bins. Yeah, we have 20,000 frequency bins, but each frequency bins corresponds to a particular frequency. And to get that, we just we look at we generate numbers from 0 to 1999, 19999, something like that. Okay. 19999. Why do we want that? Because we want the first number to be 0, and then the second number to have a slightly increased frequency, because that the second frequency bin will correspond to a slightly higher frequency. The third frequency bin will correspond to slightly higher, fourth, fifth, sixth, so on and so forth, all the way up to 2 Hz. So now we are able to have all these frequency bins. Okay. Okay, but I want them to go from 0. Okay, because now I want to start plotting, right? I want to start plotting all of this stuff out. I want to go from 0. I want this thing to be here, this thing to be here, so that we can do a nice plot. How do we do that? We just use a transpose, which is the apostrophe thing. Okay, so it's equal to frequency array. In MATLAB, transpose is just this apostrophe thing. Yeah, and this is the array that we want to have. So now we have an array of various frequencies, and these are in Hertz. These are not in whatever per second, radians per second. So I like to use Hertz instead. It's a bit more intuitive, to me at least. Hertz. And then we have our transform, right? We have our transform data over here. Okay, so let's see. Let's call this data the inlet data, equals to what? First thing will be my frequency array, and then I will have y, which is the transform. So what does this inlet data look like? I will then have all of these frequencies. Of course, they are now in complex number terms, but all the imaginary parts are 0, so essentially they are all real, and they're plotted against this what do you call that? They're plotted against this complex number part here. Okay, so all the Fourier transform data is now nicely packed, and I have them referenced against the various frequencies that I want. And if you want to do a magnitude plot, very easy. Okay, let's see. We can use this thing called magnitude, MAG of y. Mag of y Oh, maybe okay, shucks, I need to go and search it up. I can't remember what it is. Okay, so my bad. Instead of using magnitude, the correct thing is called absolute. ABS of y. It will give you the so-called it will give you the magnitude, right? Absolute. So they use the MATLAB uses absolute instead of magnitude. So let's take a look. ABSY will be here, and then you will have all this stuff. Okay, all this stuff over here, and we should be able to see a plot of it. Okay, so okay, I can do magnitude equals mag y equals to ABSY. Okay, I'm just going through some of these steps. Mag y equals mag y equals to this. Okay, and now we can actually get our peak plot. Okay, so let's do a plot of the x-axis. X-axis will be the frequency array. Then I'll do EPS-y, or magnitude of y. Okay, so this is how we get our frequency plot. And now you see that most of the things are okay. Our frequency plot is as such. Okay, we see that the most important frequency happens to be the DC frequency, because why is this so? Okay, because this is actually oscillating around 773 Kelvin. Okay, this is actually oscillating around 773, so it's over here. So the DC component is very, very big, 773 Kelvin. All right, it's a very high temperature. All right, so yeah, it's a hot industrial process, but yeah, this is the biggest part of this thing. So the DC gain is huge compared to all the other frequencies, so much so that we can't see anything at all. Okay, to help us with this, there are a few ways we can work around this. Firstly is to plot this in terms of decibels. So we'll use 20 times log 10. Okay, our numlog 20 times log 10. So this will actually give us the magnitude in decibels. So now if we plot this, okay, let's see. You should have, whoa. Okay, what's happened? Okay, hold on. Okay, so alright, so this is what we get, right? So yeah, we get this kind of plot, but oh my goodness, yes, now that's better. I think we have too many data points. Okay, alright, but what it does for you, since now everything is in a logarithmic scale, you are able to see which peaks are important. Okay, the first peak here is of course the DC peak. Okay, the DC gain is the largest. okay, but you are able to see the other peaks as well because all of them are in log scale. Again, I'm sorry, this is too many data points, so it does look very messy. But if you kind of zoom in here, you'll be able to see each of these peaks being very, very fine, as you can see here. Yeah. Okay. Long story short, we do need a way of getting rid of the DC gain if we want to see the other peaks. And there's only like one peak here, and this peak seems to be more important. Okay, this is about 4 times 10 to the minus 3. And if you know the peaks that I'm looking for, they are actually around 2 times 10 to the minus 3. This is the important peak around here. Okay, but it seems to be picking up around here. Okay, but anyway, long story short, okay, the DC gain is sort of overpowering all the other signals, so it's very hard to read this graph. Okay, except for you can see this little peak over here is at around 0.004 hertz, and this is 4 times 10 to the minus 3, which is 2 times of 2 times 10 to the minus 3. So actually, in a sense, this Fourier transform actually works, and at least you can see how putting things in decibel mode, you can actually at least have a better shot of looking at all of the other peaks, yeah, like this one. Otherwise, it's very, very hard to see anything. Okay, but this is just a way to demonstrate the new FFT code, and I want to after this want to show you my script which I used to do a new FFT and actually get a better result and deal with this whole DC component thing. Okay. All right. So yeah, let me again play this code. All right, not this one. This one. Yeah. This plot is a lot nicer than what we have before, because okay, the blue curve is the outlet. I mean the inlet temperature Fourier transform. The orange one is the output. Okay, and all of these are in so-called decibels. Okay, decibels. Okay, but I needed to subtract out all the DC gain in order to have a nicer plot. Okay, and to do that, I'll talk about it more in the next video. Okay, thanks for watching.